So for a lot of trig, unless we're doing an actual triangle problem, then we would just draw a triangle. For most of trig, we're going to set it onto an XY plane. That way, all of our diagrams will look the same. That's kind of what we want. We want kind of standard diagrams, and this is just sort of the standard way trig is done. So if you're not doing just an actual triangle, you're just drawing angles and rotations, then you're going to start with an XY axis system, and you're always going to let your initial side be from the origin and along the positive x-axis. And then you can rotate in a positive direction counterclockwise or a negative direction clockwise. So I've drawn right here. Right here we have an angle that we say terminates in quadrant 1. It's drawn in standard position, and its terminal side is in quadrant 1. And usually that's the first thing about an angle we want to know is where does it land? How far is it going to go? Is it going to go all the way to 90? Is it going to be or is it smaller than that? Acute angles will land in quadrant 1. Obtuse angles will land in quadrant 2, and then anything above 180 degrees rotation, could be in any of them depending on where it lands. So over here, the second little drawing, this angle originates along the positive x-axis and rotates more than 90 degrees and into quadrant 2. So we call that a quadrant 2 angle. That's usually what we name an angle. I go, is it a quadrant 1 or quadrant 2? So we name it kind of by the quadrant it lands in. Make sense? Okay. So what do we call the things that don't land in a quadrant? What if they land on an axis? Now in algebra, if a point lands on an axis, what do we call it? Do y'all remember? Intercept. An intercept, yeah, we call it an intercept. Well, if an angle lands along an axis, it's called a quadrantal. So a quadrantal angle is any angle that lands on an axis. And guys, it will always be divisible by 90. 0, 90, 270, 360, 540, 720, is it 720? 1080, all that good stuff, okay? So you can just keep rotating forever. But any quadrantal is going to be divisible by 90. So that's something you need to know as well.
Repeat that word, quadrantal.
Quadrantal. And hey, it's spelled wrong up here. I have an extra N. We should take that out. There we go. I need to go fix that. Nobody pointed that out yesterday. I guess you wouldn't know, would you? I didn't notice it yesterday. Quadrantal. So it's like the word quadrant, right? And then with an AL on the end. Quadrantal. So quadrantal angles are any angle that terminate along the X or the Y axis. So a complete rotation of a ray results in an angle measuring 360 degrees. If we continue the rotation, angles of measure larger than 360 can be produced. This probably most of you understand this better from skateboarding. You're like, oh, I did a 360, I did a 540. That would be like 1.5, right? Or a 720 would be 2 full rotations. So let's say those are called coterminal. That just means that they end in the same place. Terminal means end and co means together. They end together. Now how I got there might be different. For example, 60 degrees. If I just start from here and I go to 60 degrees, I'm right there, right? And that produces, this much rotation from standard position. But if I started going and I went all the way around one whole time plus 60 degrees, I would have rotated a total of 420 degrees. It was 60 plus another whole rotation. That would be 360. That still lands you along the same spot. This whole ray here, is the terminal side for both of those. So it produces the same effect, but they're different measures. But the nice thing about trig is that coterminal angles behave exactly the same way for every single thing about trig, no matter what you're doing. So if you don't want to work with an angle of 420 degrees, you don't have to. You can work with the 60 instead. And that's a whole lot easier for our brains to comprehend. If I ask you where does 60 degrees terminate, where does it stop? You tell me quadrant 1, right? But if I ask you 420, your brain doesn't automatically know that. You have to really sit and decipher it. So what we do is we take angles and we bring them either up or down so that they're between 0 and 360 so that we know where they land and we know where they terminate, and that's called coterminal. So over here I took an angle of 110 degrees, and then we rotated another whole time around and another whole time around again, and it produces 830 degrees. Does anybody know how to get there? What would I take 110 and add to it to get there? Well, to go around once I would add 360, and that would give me 470.
Okay, are you adding from like
You add from where you are. If you're at 110 degrees, okay, and I'm already right here.
360 from
And then add 360 and I'm at
470.
470. Make sense? Okay. Then add 360 again, and where do you land?
830.
830. All three of those angles are coterminal to one another. So like 110, and then where was the next one?
Like 820
No.
actually, I think.
470.
Is it?
470.
Oh.
And then if you add 360 again, you're at 830. All three of these angles, trigonometrically speaking, or these rotations, everything about them is exactly the same. It's just how many times I had to revolve around to get there. So if I'm going to work with one of those angles, which is the easiest to work with? 110, yeah. So let's talk a minute now about how to find the angle of least positive measure that is coterminal with 908 degrees. 908 degrees is too much for me. I don't have a clue where it lands. Could be quadrant 1, 2, 3, or 4. And I need to know to get started so I can start drawing a diagram and building whatever I need to build. I need to know how far from the starting point that's going to stop. To figure it out, if you just take 908 and you subtract 360 from it until you get to a number that is between 0 and 360. So what's 908 minus 360?
548.
548. So it's still too big. That's still greater than 360. So subtract 360 again.
188.
So that means that 908 degrees, did we subtract wrong? No.
No, I was going to ask if you could divide 908 by 360 and then just multiply your decimal by 360 to get your degree. You don't have to keep subtracting and subtracting.
Yes. Yes. I understood that. Yes. Another way to do it, what you just said is you can take the thing here, 908, and divide. If you say 908 divided by 360, what does that give you? You said
2.5
2 point,
2.5 2 repeating.
like that?
Yes, ma'am.
Okay. Another way to do it is if you do that, and it just depends on what kind of calculator you're being allowed to use. That's why I caution you about that, because if it is a repeating decimal, some calculators can handle that and some can't. Does that make sense? Okay. So another way is you could say 908 minus 2 times 360. And tell me what that equals, and it'll get you there too. So like if you ignore the decimal and you just say 908 minus this times that, and I've seen students do it that way as well. That will also get you to 188. But yeah, what you said will work for sure. Okay? Does that make sense to you guys? Yes? Okay, so you're going to need to be able to do that. You're going to need to be able to take any angle and figure out how to get where you want to go. You know, you want to get it up to an angle between 0 and 360. So those are using coterminal angles. Okay. So let's do it with a negative and see if you can figure it out. Negative 75. Take negative 75 degrees, and I want to know what's the closest thing coterminal to it. Well, first off, I don't want to subtract 360 because I do. I'm just making it worse, right? So the nice thing about it is it doesn't matter what direction you go, positive or negative, you're going to land in the same spot. So this time we can add 360 to it and bring it back up to where we need to go. What's that land me at?
285.
285. What quadrant is that in?
3.
We haven't talked a lot about it. Let's see.
No.
Okay. We know that it's in 4 because that goes from 0 to, this is 90. This is what? 180. What's the next quadrantal? You may not be as familiar with that. That's 270, yeah, 270. And this is 360 again, like we get all the way around. So 285 degrees is going to land us somewhere out here. So negative 75 then is this much. And that would make this much 285. So I think it's a pretty useful concept there. Any questions about it? Seems pretty easy? Okay. I need you to get accustomed to, well, no, I guess we're going to do another problem. Of all the things in this section for your book to decide to do 2 examples of rather than just 1, I wouldn't have thought it would be this. Because I think this is pretty self-explanatory. Take negative 800 degrees and try to bring it up to a positive angle. You want the least positive angle. So if we start at negative 800 and we add 360 once, where are we?
440.
440. But we're still in the negatives. Okay? But we know that negative 800 and negative 440 are coterminal. Now add it again.
Negative 80.
Negative 80. Okay? So that means that negative 800, negative 440, and negative 80 are coterminal. Trigonometrically speaking, they behave exactly the same way as one another. Then we're still in the negatives, so if you add it again, it brings you to yet another coterminal of 280. That's usually the one people are trying to get to. They want to know what's the first one that's positive, because then I can look at it and tell what quadrant it's in. Sometimes you'll see things very generically written, and we won't use this except for a few times kind of later on in the semester. But you'll sometimes see people and they'll take you can take any angle that you want, and you can say that if you want to generate a list of all of the coterminals, then you can do that by writing it generically as, say, like the angle plus however many times you want to wrap around, how many times you want it to rotate, times 360. So, like, for example, if I were going to say I want something to stop 55 degrees away from where it started, then I could say, all right, but I only want to allow it to go around 3 times, and then I want it to stop forever. Then I could say 55 plus 3 times 360. And tell me what that equals. 55 plus 3 times 360. 1135? Yes? Okay. Then I would need to figure out a way to program whatever it was I was building to stop after it rotated 1,135 degrees. I would want it to stop forever and then, be done, not go any further. So that's how, if you know you want it to go a certain angle, but then you want it to wrap around so many times from there, that's how you would, program it in. Kind of neat, huh? So for the example they gave you, they said, if you wanted, you're taking 60 degrees as your set angle, and you wanted to wrap it around twice, you would do 780. But if you only wanted once, you would do 420, And then if you wanted it no times, it would bring you back to the 60. You just wanted it to go one time and not a complete revolution, and so on. So if you just want a generic way to generate them, that works. We don't use it very often unless we're solving trigonometric equations. You'll see this used a little bit down the road. Okay, so we know that CD players always spin at the same speed. Suppose that we have one that goes 480 revolutions per minute. I want to figure out how many degrees a point on the edge of a CD will move in 2 seconds. So first off, we know that 480 revolutions per minute is what I was given, correct? But we need to convert that not to minutes, but to seconds. I need to know about the seconds. So that means that I have to multiply that by 60, and there are 60 seconds in 1 minute. Okay? Am I done? Oh, guys, I did that backwards. My train tracks are upside down. Hold on. Okay. I want the minutes on top, right? Yeah. There's 1 minute in 60 seconds. Okay? Am I done? No. Now I have to convert it to what? That will,
You're,
I need to convert it to degrees, right?
oh yeah.
So you multiply by 360 degrees in one what? Revolution, yeah. And so that's from that. Have y'all ever learned that through dimensional analysis? So if it doesn't just come naturally to you, you can do it through dimensional analysis. And so the minutes will cancel, and then the revolutions will cancel, and that will leave you with degrees per second, okay? But then that'll be how many in 1 second. So now you have to multiply it by 2 seconds. And that gives you it's 5,760, right? So that's how far it would rotate. As some of you pointed out, there's a much easier way to do that if you can just kind of, it makes sense to you, but if it doesn't, you can always do dimensional analysis to get you there.
Well, see,